The next topic we're going to cover is this idea of inertia. And inertia says, well, how hard is it to rotate something? So the larger the inertial value of something means the more oomph it takes to get it going. And if you look in your book on page 210, you'll see a collection of shapes and pictures of those shapes, and then a set of equations that go with each of those shapes. So that's pretty much what you're going to be using. But what we can do is take like a collection of these things and add them together and say, okay, so if I put those things together and I want to say rotate them about some mass or about some position, then I can figure out how hard it will be. What is the inertia of this system to get it to rotate? For center of mass, if I had something like this, I'd figure out the center of mass and I'd figure out the place that it would rotate most naturally. So where is the most concentrated position for this center of mass for this system would give me, if I let it go and then give it a shove, what is it most likely to rotate around? And remember I said in the previous videos, that's going to be closer to the highest concentration of the mass for that system. For humans, that's right around our torsos, right? We have most of our mass in our midsection. And so when we rotate, if you look at a diver or somebody doing gymnastics, they're rotating around that pivot point around their hips. That is the natural place for them to rotate. So for a point particle, what we say is this is the mass of the point particle. This is the distance from rotation, the axes of rotation. For all of those other shapes, the cylinder is probably the most common one we use. So for the inertia for a cylinder, I cylinder is 1/2 mr squared. Now, if this were calculus, we'd be able to do some integration and figure out where all these equations come from. But seeing as this is not, you get to use the handy-dandy table. But what we will do is generally we won't have just one thing rotating, it's a collection of things rotating together. And that's where we do something like this. So this says that the inertia of a system is the sum of all of the inertia. So very much like our center of mass, but you'll just see here that instead of dividing by mass, it's just the mass of each thing times the distance away from the axis of rotation squared. So we would do that and then add up all of the inertias to figure out what the inertia of the system is. So in one of the first examples I gave you in your handout, this would be 7-2. I have a mass here, and this is going to be the axis of rotation that I gave you. Let's see, a mass here, and a mass here, and a mass here. And I tell you that this is 1 meter, and this is 0.5 meters, and this is 0.5 meters. Did I give you the mass of these things? I don't think I did. Oh, I did. All masses are 1 kilogram. So mass equals 1 kilogram. Cool. So for this, if this is my axis of rotation, then what do I have? I have, let's just call this, oops, I did a different color. Let's call this 1, 2, 3, and 4. So the sum of my inertias gives me mass 1 times 0 squared. This is the R, it's on the axis, that's where I'm rotating about. Plus, let's see, plus mass times, well, this is 1 meter away, meter squared, plus 1 times, this is also 1 meter away, squared, plus this is 1, so this is 1.5 meters away. So this is also 1 kilogram times 1.5 meters away, squared. So did it bug you that this thing is below axes and I looked at the R and I said it's just 1? So the neat thing about this is if this thing, and I should have made a different color, this isn't something that I came up with, this is in the drawing. So it's saying I want to rotate this system. So it is a direct line radius. So this distance is just a direct line from this thing, that this thing would be then kind of rotating out of the page and into the page and out of the page and into the page. So it is the distance from this rotation. So I get to this and I get 1 plus 1 plus, ooh, need my calculator, 1.5 squared plus 2.25. And it is only 1 plus 1 because these are all 1 kilogram masses. So then 2 equals 4.25, and let's see what these units are. This is a mass, that's kilograms times meters squared. So my units for this gives me something in terms of kilograms meters squared. Unlike something like newtons, we don't have a handy dandy, real simple abbreviation for this. So that's how hard that is to rotate. Now what happens if we take this exact same picture and this time we want to rotate it on this side? I'm going to use a different piece of paper to do this. Or do I need to? No, I don't. So if now, let me do a different color. Just clear what I'm talking about. Now if I take this pole and move it over here and rotate this thing now going out and into the page, going this way. So this one would be for, this 4.25 would be for this one. What do you think is going to happen when I do it for this one? Now that mass is there. You expect that the inertia will be larger or smaller. Think center of mass. And in center of mass, I said things are going to tend to rotate about where most of the mass is concentrated. So if that is where something would naturally rotate, if I make my axis of rotation closer to something center of mass, I lower the inertia. So let's see if that's true. Because here, let's see, I feel like I'm closer to these three and I only have one kind of dangling out there. Let's do it in, let's go with black. So the sum of my inertias then is going to equal, that one is times 0, so mass times 0 squared plus, let's see, I have these two at 0.5, so 1 times 0.5 squared plus 1 times 0.5 squared, oops, sorry, 0.5 squared plus 1 times 1.5 squared. Again, it's because I've said all of the masses are 1. I should have just written that as a 1. Sorry about that. All of the masses are 1 kilogram. So let's say 0.5 squared, 0.25. So I get this as 0.25 plus 0.25 plus 2.25. So 2.5, 2 3/4, 2.75 kilograms meters squared. So it will be easier to rotate this if I change this axis over here. Now, what do you think will happen if in the next example, well, the next example chooses down here. I want to choose rotate here. Yeah, so what if I put an axis of rotation straight through here? What is that going to give me? Well, that seems like that's going to give me like my tiniest inertia, which would make sense because it would be like me putting just a rod through here, so I have just one mass and a small distance away. So if I change the axis of rotation to be straight through these masses, that would give me like 0.25 kilograms meters squared. So that would be the tiniest, but in part because I'm eliminating all those masses. So it's not really a fair comparison. But the next one, then it says, what if I rotate about here? So what if I rotate about here? So if I change this rotation, and now I choose like to rotate it here, well, what am I going to get? I have from this axis, everything is 0.5 meters up. So I'm going to end up with 0.5 squared. I just wanted to double check. I have 0.5 squared for each one. and they're all 1 kilogram. So that then to rotate here would be 0.75 squared. I'm sorry, 0.75. So 0.25 plus 0.25 plus 0.25 gives me 0.75 kilograms meters squared. So think about why that is. So now I have all of the masses really close to this distance. From here, I had these masses, I had a mass 1.5 meters away. So I expect that this would be smaller because all of these 3 masses were closer to the axis of rotation and it was only one that was way far out. This one, I had 3 masses 1.5 meters out. If I rotate here, I have these 3 masses are only within that 0.5 meter. So my I for that one just becomes 0.75 squared for rotating here. Awesome.